Hi everyone. I am Zhu Kaifan from Nanjing University of Science and Technology, China. I am very excited to introduce our recent work, Depth-Centric Dehazing and Depth Estimation from Real-World Hazy Driving Video. If you want to know more details about this work, please scan the QR code in the top right corner. Existing video dehazing methods are primarily trained on synthetic datasets, limiting their effectiveness in real-world foggy scenarios, with MapNet being a representative example. In contrast, the DVD method is trained on real datasets and achieves satisfactory dehazing results in real-world conditions. However, its slow inference speed hinders practical application in real scenarios. In real hazy scenes, both RGB visibility and LiDAR perception are limited, with no ground truth data available for model training. Therefore, we explore solving dehazing and depth estimation using non-aligned references. Additionally, we observed that the atmospheric scattering model and reprojection constraints in self-supervised depth estimation inherently form mutual constraints. This synergy enables models to learn more stable and accurate target distributions. Given the complementary nature of these tasks, we jointly address dehazing and self-supervised depth estimation, as expressed in the proposed unified formulation. As illustrated in Fig. A, B, C, and D, preliminary experiments validate that jointly solving video dehazing and depth estimation enhances both tasks' performance. Building on this insight, we designed a depth-centric joint learning framework for dehazing and depth estimation. Firstly, the framework demonstrates that the reconstruction loss based on the atmospheric scattering model introduces additional constraints for self-supervised depth estimation through brightness consistency. Accurate depth further aids in decoupling scattering model parameters, enhancing dehazing results, making the two tasks complementary. Secondly, self-supervised depth estimation relies on the photometric consistency assumption, which requires consistent pixel brightness across consecutive RGB frames. We regularize the depth estimation network using depth from non-aligned clear reference videos, simultaneously imposing brightness consistency constraints to prevent flickering between adjacent frames dehazing. Thirdly, DMFire enhances high-frequency detail recovery in dehazed video frames, while DMDR addresses black hole issues in depth estimation caused by weakly textured regions. Finally, in real hazy scenes, scattering does not always conform to an ideal model, as beta depends not only on wavelength but also on the size and distribution of scattering particles, e.g., patchy haze. Therefore, we assume beta to be a non-uniform variable. The results under unpaired, paired, and non-aligned settings are summarized in table. Overall, DCL ranks first in both fade and Nike across all methods, and our method achieved the shortest inference times of 0.075 s for image video dehazing. While these methods generally yield visually appealing dehazing results, DCL restores clearer predictions with more accurate content and outlines. Additionally, it is capable of estimating valid depth, a feature not offered by other dehazing models. Due to the scarcity of hazy data with depth annotations, we trained these methods on the GoPro Hazy benchmark and evaluate them on the DenseFog dataset. It is worth noting that, during the testing phase, our DCL only uses the depth estimation subnetwork. Table reports the quantitative results. Overall, in both light and dense fog scenarios, our DCL outperforms the others across nearly all 5 evaluation metrics. As shown, the depth predictions from MonoVi-T and MonoVi-Fi are blurry and unreliable, while our DCL generates more accurate depth estimates and also provides cleaner dehazed images. Both quantitative ablation evaluations and visual results demonstrate the significant impact of the proposed modules, DMFire and DMDR. These modules show clear improvements, especially in weak texture areas and small distant targets. For the different tasks dehazing and depth estimation, we also provide task-specific ablation visualizations. The results show clear improvements with the proposed modules for each task. We conducted a comparison experiment with different values of beta constant versus non-uniform. The results show that a non-uniform beta leads to better depth estimation accuracy, and we also provide visual comparison results. In previous studies, beta was defined as a constant, simplifying the atmospheric scattering model. However, in DCL, we consider a more realistic atmospheric scattering model, where beta is defined as a non-uniform variable to better align with real-world scenarios. Experimental results show that the predicted depth outperforms the reference depth. This is mainly due to the significant constraint imposed on depth estimation by the atmospheric scattering model through the reconstruction laws, while the reference depth is obtained by mono-depth 2 from the reference non-aligned clear video. From the video demo, it is clear that our proposed method DCL outperforms current state-of-the-art video dehazing methods in terms of both better dehazing results and the stability of the dehazed video, i.e., minimal flickering and jitter between consecutive frames. Compared to the current state-of-the-art self-supervised depth estimation methods, our approach achieves better depth estimation in real hazy scenes, especially in weak texture regions and in terms of depth quality. In addition, we have provided video demonstrations for the ablation of core modules. These demonstrations allow us to observe the impact of the proposed modules on dehazing image quality and depth estimation accuracy. It is evident that the proposed modules significantly enhance performance in both dehazing and depth estimation. For more details about our work, please refer to our paper, project homepage, and code. If you have any questions, feel free to reach out to us. Thank you.